Welcome to another explainer. So, have you ever paused during your morning commute and just kind of wondered, how exactly does my car or motorcycle convert a tank of boring, static liquid fuel into the high-speed motion that actually propels me down the highway? I mean, it literally feels like magic, but it's actually one of the absolute most brilliant mechanical achievements in human history. Today, we're going to completely demystify the four-stroke internal combustion engine. We'll break down exactly how this perfectly synchronized mechanical dance harnesses thousands of controlled explosions every single minute just to get you where you need to go. All right, let's dive into this. We're going to look at this process as a sort of chronological four-act play. First, we'll meet the mechanical players. Then we go through the four strokes. Stroke 1 is the intake, stroke 2 is the compression, stroke 3 is the power, and stroke 4 is the exhaust. And finally, we'll wrap up with how the continuous engine cycle actually works.
Okay, part 1, meet the mechanical players.
Now, before we can really appreciate the performance, we've got to understand the stage, right? And that stage is the engine block. This is a solid, incredibly rigid framework, usually cast from iron or aluminum, and it's built to withstand some absolutely extreme forces. If you look at a cross-section, the main arena is that perfectly round, polished chamber right in the center. We call that the cylinder. It's inside this super confined, heavily reinforced space that our entire four-stroke cycle is going to unfold, containing and directing all that massive energy from combustion. So let's meet our key mechanical actors. Inside that cylinder is the piston, basically a cylindrical plug that just slides up and down. That simple linear motion, that's the entire foundation of our mechanical work. Now the piston is attached to a connecting rod. Think of it like a mechanical wrist that transfers the piston's downward force straight to the crankshaft. And the crankshaft is just ingenious. It takes that straight up and down motion and converts it into the rotational, spinning motion that actually turns your wheels. Up above the piston, acting as the control center, we've got the valves. These are the engine's breathing controls, letting air and fuel in and exhaust out. And finally, sitting right at the very top is the spark plug. That's our high voltage catalyst, just waiting to trigger the explosion. Moving on to part 2, stroke 1, the intake. Let's open the curtains on the first act of our play. The cycle kicks off with the piston sitting at the very top of the cylinder. As the crankshaft rotates, it pulls that piston downward. And right at the same time, the intake valve, acting kind of like a perfectly synchronized trapdoor at the top, opens wide, while the exhaust valve stays completely shut. Now you might be wondering, how exactly does the fuel get in there? Well, it isn't magic, it's just basic physics. As the piston drops, it increases the empty volume inside that sealed cylinder. This causes a sudden drop in pressure, creating a manifold vacuum. We're talking a pressure drop of about 0.1 to 0.3 bar compared to the outside atmosphere. Because the atmospheric pressure outside is now higher than the pressure inside, a precisely measured mix of fuel and air is literally sucked or pushed right into the cylinder. By the time the piston hits rock bottom, the cylinder is packed full of a fresh combustible charge.
All right, part 3, stroke 2, the compression.
So the intake valve snaps shut, completely sealing off our arena. The piston, which just hit the bottom, reverses direction and starts surging back up toward the top of the cylinder. And since there's absolutely no way out for that air and fuel, they're being forcefully squeezed together. The really crucial moment happens right as the piston hits its absolute highest peak. Mechanics call this top dead center, or TDC. That mixture we sucked in earlier, it has now been drastically squeezed into a tiny space. We're talking anywhere from a 1/7 to a 1/12 of its original volume. This extreme compression violently skyrockets both the internal pressure and the temperature of the mixture. Basically, it makes the fuel highly volatile and perfectly primed for a really efficient combustion.
Next up, part 4, stroke 3, the power.
Okay, so the stage is set. Everything is sealed tight, the pressure is immense, and the temperature is peaking. At the exact fraction of a second when the piston hits maximum compression, a high-voltage electrical signal is shot over to the spark plug.
The spark plug fires off, delivering an intense jolt that instantly ignites that highly volatile, super-compressed air-fuel mixture. And what follows isn't some slow burn. No, it is a rapid, highly controlled explosion, right there inside the cylinder. The sheer violence of this combustion is actually staggering. The expanding hot gases reach searing temperatures of up to 2,500 degrees Celsius, and the pressure spikes to as much as 900 psi. Desperately seeking a way out, this rapidly expanding gas slams into the literally only movable object in the chamber, the top of the piston. It blasts the piston downward with a mind-boggling 4,000 pounds of force. That tremendous downward thrust acts on the connecting rod, which forcefully spins the crankshaft. We really need to pause here for a second to realize something incredible. This is the only stroke that actually produces power. Think about that. The intake, the compression, and the exhaust that's coming up next, they all exist for one reason only: to set up this singular, violent fraction of a second that actually generates the mechanical energy to drive your wheels. Which brings us to part 5, stroke 4, the exhaust. So after that massive explosion, the stage is, quite frankly, a mess of spent hot gases. But the crankshaft's momentum forces the piston back upward one last time. Only this time, the exhaust valve opens up. The rising piston acts exactly like a plunger, physically shoving all those leftover burnt gases right out of the cylinder through the open exhaust port. Notice how beautifully the engine's breathing controls adapt here. During the power stroke, both valves are locked down tight to contain those 4,000 pounds of force. But the second we transition to the exhaust stroke, that exhaust valve springs open because there is still a ton of residual pressure in the cylinder. Those 900 degrees Celsius spent gases are blasted out into your exhaust manifold at literally the speed of sound. By the time the piston reaches the top, the cylinder is totally clear, the exhaust valve closes, and the stage is perfectly reset for a brand new intake stroke. And finally, part 6, the continuous engine cycle. Okay, so we just established that out of the 4 strokes, only one of them, the power stroke, actually produces any energy. So a logical question is, why doesn't the engine just abruptly stop, or at least violently jerk, during the intake, compression, and exhaust strokes? Well, simple physics provides an incredibly elegant solution, and that is inertia. Attached to the end of the crankshaft is a heavy, rotating metal disc called a flywheel. You can kind of think of it as a mechanical battery. When that massive 4,000-pound push from the power stroke spins the crankshaft, the heavy flywheel spins right along with it, storing up all that rotational kinetic energy. Because of its heavy mass, it naturally wants to keep spinning, and that stored momentum literally drags the piston through those other 3 non-productive strokes until the very next power stroke hits. This entire process loops into a continuous, repeating 360-degree dance, which is mapped out perfectly on a valve timing diagram. Intake, compression, power, exhaust. Breathe in, squeeze, bang, blow out. In a typical car engine that's just cruising down the highway, this incredibly precise 4-stroke ballet is happening thousands of times every single minute, across multiple cylinders, and it's all perfectly timed to fractions of a second. It really makes you look at your vehicle entirely differently, doesn't it? The next time you turn the key or press that ignition button, take just a brief moment to appreciate the sheer mechanical magic happening right in front of you. You are commanding thousands of violent explosions, wielding thousands of pounds of force, all synchronized with fractional second perfection, just to go grab a cup of coffee. When you really stop and consider all that mechanical fury happening right beneath the hood, isn't it an absolute miracle that your morning commute is so quiet? Thank you so much for joining me for this explainer. Keep learning and stay curious.